Let's talk about the things we've got going on this week. So we have we'll have a quiz next Friday. We will have, I've got help sessions. There'll be a help session next Thursday evening, 7:30 p.m. on Google Meet. And then next week I have appointments. Appointments Monday and Wednesday, 1 to 5 p.m. Okay, just let me know in class for those if you'd like to come see me. And then there'll be a homework due on Monday morning at 7 a.m. I just wanted to ask, I looked at the homeworks. I saw a number of homeworks where people had started them but had lower scores on them. I wanted to just check with everybody. I've set my settings say that you're allowed unlimited attempts. Does anybody have any problems with that? Okay, and I have a couple people that have reported to me problems with getting to the homeworks. Hopefully, if you're having problems, you need to let me know, right? If you've tried to get to homeworks and you haven't been able to get to them, and that's why you haven't, if you haven't done one, that's why you haven't done one. Follow up with me and we'll fix that. Okay, even if it's a past homework. So, I don't want anybody to miss credit on those homeworks because of technical problems. All right, so what we've been talking, any questions on what we're doing in class? All right, then we'll go on. What we're going to be doing, what we had your test is you had limiting reagents we've been talking about, and we've also been talking about solutions. And the last problem on the quiz was a dilution. I want to expand on what we talked about last lecture. And so when we think about dilutions, I just introduced it, so I was careful to not do something where you had to change units. But what I want to talk about is we've got this equation for dilutions, M1V1C1, M1V1, let me start over, M1L1 equals M2L2, okay, right? And where we've got this is molarity, and this is liters. And remember, where this thing comes from is the molarity is equal to the moles divided by the liters, right? I can multiply both sides of that equation times liters. And what I get out of that is liters times molarity is equal to moles. And what this tells me is that if I change the volume of my solution, I call this one and this one, and if I go and I change this one, I change something, I add some volume, the moles don't change. They're not leaving my container. They don't go anywhere, okay? So if I add more volume to my container, what's going to happen is my volume might go up, and then my my concentration has to go down. All right, so my example was lemonade last lecture. You could imagine when I go to sheets, sometimes I order the, I don't know, it's a standard or whatever. It's not the very small, but it's the second size up. That's the one I should always order. Sometimes I order the one up, and I always wonder whether they're grinding the same amount of beans for each and just adding more water, right? And I can't taste the difference. I'm not that sensitive. I know people that are. I might have been a chef if I was. But, so we're not changing the amount there. But if this goes up and we haven't changed how much is in there, the amount, not the concentration, then the concentration has to go down. Hopefully that makes sense intuitively. All right, but this is actually, so we did this for molarity and moles, but this is a more general concept. As long as my units match, I can do this we can do this generally. So this is C2V2. So this is going to be concentration. And it can be concentration in any units. Okay? And this can be volume. And I keep saying volume for the liters, but it can be volume in any units. And this works as long as the units match. So units must match. And units must match. And you will use this over and over and over again in your chemistry career. Okay? Super useful equation. Gets used all the time, especially if you end up working in a lab somehow. All right, so let's go ahead and take a look at an example of something like that. So chemists don't always use molarity. Sometimes so I'm a biochemist. Biochemistry, molarity is a lot. Molarity is a mole is a big, it's like a handful of stuff. Okay, I work in little tubes. Actually, I work on the computer now. But but before that, I worked in little tubes. So I'm only doing small amounts, and I'm only doing small concentrations because nothing's 1 molar, nothing's 1 molar, 5 molar, or anything like that in your body. Okay, but let's say so what I could do. Though let's say I've got some other units I'm working at, and my students in biochem are writing up a lab right now where they're working, their concentration is milligrams per milliliter. Okay, so it's an amount in grams per milliliter. Great. Well, let's say we've got that. They're working with an enzyme called lactate dehydrogenase. If you have a solution of, let's say, 1.2 milligrams per milliliter of lactate dehydrogenase. Let's say you have, not if, because I want it for proper sentences. You have a solution of what is the concentration if you dilute 10 microliters of this solution, that's a millionth of a liter, to 100 microliters. Okay, and when I talk about this is exactly what they had to do in lab, but I didn't tell them. They had to figure out what dilution they wanted to make. Okay, but more fun experiments when you can actually make your own decisions. All right, so we've got a solution here. We've got a concentration here that's different, right? We've got microliters. We can turn that into liters, but we don't need to get our concentration as long as both of our volumes are in liters. So the way I would set this up with C1 V1 C2 V2, I have, this is my concentration, right? What volume does that go with? What volume has a concentration of 1.2 mg per mil? The 10 microliters, right? That's the thing I'm diluting. So I have 1.2 milligrams per milliliter of lactate dehydrogenase. I have 10 microliters. This is a micro. And then I have some new concentration that I don't know, and then its volume is 100 microliters. All right, these units match, and the other units need to match. I don't have the units for C2. What are the units for C2 going to be? Milligrams per milliliter, because this and this are going to cancel, right? They're on the, we've done cancels above and below, right? This divided by this. If they're on, if we've got something on each side of the equation, we can cancel it. All right, I won't do it, but I could also take a 0 off each side. Because there's a 0, that's like dividing each side by 10. All right, I'm trying to find my calculator, but I don't really need it for this. I'm going to divide both sides by 100, right? Okay. Let's just do it though. So if I divide both sides by 100, we already canceled our units. That cancels, giving me C2 alone. I can get rid of one of these zeros, right? A 0 on top, a 0 on the bottom. And then I've got 1.2 divided by 10. Even this morning, my sleep-deprived Friday state, I can actually do that one in my head. Okay, because it's a 10. So then my answer is going to be 0.12 milligrams per milliliter. Does that make sense? I'm not going to spend more time on one of these, but that's the general format. These units could be anything. This could have been in quarts. Okay, while I was prepping my lunch this morning, I thought of a great problem for this, but I'm not going to do it. This concentration could have been minutes of Elmo per Sesame Street episode. Okay, and then my volume could have been how many Sesame Street episodes. And if I add more Sesame Street episodes without Elmo, I'm diluting Elmo. As long as those units match, it still works. Questions? How to do that? All right, so more general form. Just use the more general form from here on out, okay? All right, the only thing that you need from the other equation, you don't even need the M1, L1, M2, L2 anymore, okay? What you need, but you do need to remember that molarity is equal to moles divided by liters, because that will come up again. Questions? All right, then I want to talk about a concept called serial dilution, which is another thing we do in lab. All right, sometimes you dilute something and you can only dilute accurately so much in one shot, and so then you need to dilute it again, or you dilute it and you decide that you didn't dilute it enough based on what measurements you're making. So serial dilution. Serial dilution is when you dilute a solution and then you dilute the diluted solution, and you might repeat. All right, so that'd be like for my lemonade example, I added water, and then if I took some of that lemonade, diluted lemonade, and put it in a new glass and added some more water to it. This can repeat many times. A place you probably haven't seen it yet, but how many people are going to take a bunch of biology? Okay, for those of you who are going to take a bunch of biology, one of the things you do in microbiology is that you try and figure out how many bacteria are in a sample, right? So I could, let's say this table was a mess. I don't know how, I've not done this, so, but if this table was a real mess, I might be trying to figure out, I might have a lot of bacteria on it, right? Let's take some food. Let's take some food that's been in your fridge way too long, okay? And you decide to swipe it. It's got bacteria on it, not mold, all right? And you put that in the solution, dissolve it. Well, you might go ahead and then plate the bacteria, plate that solution on a plate. I don't know if you guys have seen this before, but what you can do is you can take a plate that essentially has Jell-O in it, and what it does is every place a bacterium lands on it, it sticks, and then it doubles and makes 2, and they make 4, and they make 16, etc., until you have millions. And once you have many millions, you can actually see a spot of all the bacteria growing on top of each other. Right? Okay? So now imagine I'm doing this and I actually have a lot of bacteria in my sample. Let's pretend it goes across the whole thing. Okay? Because I don't want to draw this all the way. And I have even more a lot of bacteria across my sample. When you have them separate, you can count how many bacteria there were because each one of these spots came from a single bacterium. But if I continue to add bacterium, eventually they're all on top of each other and I can't see that, right? So I took my swab off a piece of something from my fridge that bacteria could grow on. Let's say it's the surface of, let's say it's an apple that had some liquid in there. Some liquid exposed. I went and I swabbed that, I put it in, I've got too much bacteria. I do my plating and it's what we call a lawn. It just looks like that. So I can't count individual ones. Well, what I can do is I can take that original sample and I can dilute it 1 to 10 and also put that on a plate, right? So I put that on a plate, and that also gives me a log. So then I take, so this was my, well, in chemistry, I don't know if they call it neat in micro, but we would call this neat, okay? Undiluted. This would be my 1 to 10 dilution. It's still a log. So then I would take it, I would make a 1 to 10 dilution of that. Now I would have a 1 to 100 dilution of the original because it was a 1 to 10 and then a 1 to 10. You see that? Okay? And so now maybe I would have, let's do it to the one. I can sort of count, but there's still too many that are kind of on top of each other. And then I can do that again. And essentially, this is a technique you do in microbiology if you're trying to figure out how many bacteria are somewhere. You get a sample, you plot, you put it on a plate straight. You make a 1 to 10 dilution. You make a 1 to 10 dilution of your 1 to 10 dilution for 1 to 100. You make a 1 to 10 dilution of your 1 to 100 for 1 to 1,000. Okay, microbiologists have a good feel for how many of those you would need to do because you don't actually wait because they take a day to grow, right? You plot maybe even more depending on what bacteria you're looking for. But you do all of them, you put them all on plates and you look for them. See the use of a serial dilution? There are lots of uses for serial dilutions, but that's an example of that. All right, so let's go ahead and do a calculation of this. You have a 1.48 molar solution of, let's do magnesium nitrate. You take, let's say you take 10 milliliters of this solution and dilute it to, let's say, 45 milliliters. What's the concentration of the new solution in molarity? I'm not even going to say in molarity because that's going to be your default, not because it's a chemistry class and it's molar, but that should be your default because the units match, right? If I don't ask you for specific units, take the easy ones, the ones that just pop out of the problem. Go ahead and solve that one, and I'm going to get my things subscripted, and then I'm going to extend the problem. All right, so if you haven't finished the top one, if you finished the top one, do the next one. This is just an example of a serial dilution and how you would do these calculations. You're going to be using C1, V1, C2, V2 here. Okay, I'm going to just come around while you're working on that. Look forward if you've done both already. is just I'm going to check and see what your first one is. Actually, your first one is.
You can multiply them out. And then you need to do it. So you're trying to solve for the granularity that you move up L2 as you move on. Yep. So what are you going to do with this? Yep. You want that. Okay. So if you
Arrange the equation. All of these problems are going to be, you've got three of them, and you do know the other. You try to find the other. So you've got C1 V1 equals C2 V2, and if it's a dilution problem, you're going to have C1 V1 equals, we're solving for C2, and you divide both sides. Whoops, divide, not multiply. Divide both sides by V2. Okay, let's go ahead and look at this. So first one I just did, I'm gonna erase that and just do it again. So one way you can do this, when I started teaching, I would actually solve all my problem. I would solve my things generically before putting the numbers in. And so that's what I was kind of doing right there. I think people find it easier to have the numbers and do it. But so what I've got, my first solution, remember what's going to be a C1 V1 equals C2 V2 problem. I have a 1 molar, 1.48 molar solution. That'll be my C1. What's my V1? Which V goes with it? The 10 milliliters. So that's the trick here. Which one's my V in this type of problem? Which one's my V1? Which, you could have three things, two are going to go together and one is not, okay? And you need to get them separated. Also making sure your units match, which we haven't really worried about here. So I'm trying to solve for my new concentration, and my new volume, my final volume is 45 milliliters. What this means in the lab, what I've done is I have 10 milliliters, and I'll say water probably, and I'm going to add 45, I'm not going to add 45, I'm going to add 35 milliliters to get 45 total when you see this, okay? It's not that I add 45 like I almost said. I have 10 milliliters to start, and when I'm done, I have 45, which here I would have added 35. So this ended up being, I've got 3.3. Or no, 3.3. So that C2 equals 3.3 molar. No, that can't be right. 0.33. Yeah. Oh, okay. 3.33 molar. Why did I say it can't be right? This is a number sense thing. So whenever I'm doing these sorts of things, I'm checking, right? You should try to practice checking. I put it in my calculator. I got number out. Does that number look right? Okay, just it's kind of going all the time. Why was 3 wrong?
Because it can't be more than the original.
Yeah, it can't be more concentrated. If I add water to some solution, it doesn't get more concentrated ever. So the fact that it was 3, I knew it was wrong. All right, so that's the answer to my first one, right? And then for my second one, I'm doing a serial dilution. I'm going to take this solution, I'm going to dilute it some more. Jude?
So to get 0.33, you divided
Yes.
C1 and V1 by V2.
Yes. So
C2.
yes. So let me do that. So what I did to get my 0.33 is that I'm trying to get C2 by itself. So I'm going to divide both sides by 45. Okay, and so 45 milliliters and 45 milliliters cancels over here. Over here, I've got a milliliters can cancel with a milliliters, which is going to leave me just with molar for my units, and then 0.33 is what I got out of that. You got 0. Let's check it later. Yes. Or are you telling me what your 0.48? Yeah, let's check it later. Okay, so then, unless other people got 0.48. Okay. So then we do our next solution. I'm going to take 30 milliliters of the next solution. So my C1 is 30 milliliters. What is my V1 is 30 milliliters. What is my C1? 0.33. It's the concentration from the previous dilution. And then I'm trying to find my C2 again, and I diluted to what? 200, right. So that means I added 170 milliliters of probably water. We're not saying what the solvent is, but Gen Chem, it's kind of always going to be water. All right, to solve this, once again, I'm going to divide both sides by 270 milliliters. 270 milliliters cancels with 270 milliliters. Over here, milliliters cancels with milliliters.
Where'd you get the 270?
Oh, sorry. Thank you. 200. I was just checking you guys are paying attention. And then 0.33 divide times 30. 200. I got 0.0495, and I'll do sig figs on that. How'd I do? Okay. So C2 is equal to, looks like we got two significant figures here. So 0.04, well, it's going to be 50 actually, rounding. 50 molar. Questions? Okay, that's a serial dilution. And like I said, for this microbiology stuff, you might do it a whole bunch of times. Okay. All right. We're going to move on from serial dilutions. And I want to talk about solutions. While we're talking about solutions, let's talk about solution stoichiometry now. All right, so for solution stoichiometry, when we've been doing stoichiometry before, we've had various things we can do, but our general path or our most common path is grams to moles, let's say A, to moles of A, to moles of B, to grams of B, right? That's our usual thing. But remember, we've also had other things. We can go molecules. We've also done that as well. Let's go ahead and we'll add it. So these could be double arrows. They can go either direction. We've also had where we talk about molecules and molecules. So here we would use Avogadro's number. All right, remember that this is our formula weight of A. This is our formula weight of B. What I'm drawing in here, these are the conversion factors we're going to use to go from one to the other. This right here is the whole number ratios from the chemical equation. So ratios from equation. Okay, and then up here we had Avogadro's number. Okay, that should be all review. And then what we're going to add today is we'll add something new. We're going to add volume of A. And over here, we're going to go volume of B. Right, and you could do all these sorts of things. We're going to go ahead and probably do a volume of A to volume of B problem, But I could go volume of A to grams of B. I could go volume of A to molecules of B. All right, but if I want to go from volume to moles, how am I going to do that? I'm going to use my molarity is equal to moles over liters, right? I'm going to use my concentration. So we'll say for now we'll say concentration. So more generally, it could be concentration of A and concentration of B, and we could do more complicated problems where we go from any sort of concentration units. I think we're not going to worry about that. We're just going to worry about molarity. All right, we'll just do this with molarity here. But so let's think about how we would do that. So when I think about concentration of A, I've got a volume, right? And what the molarity tells me is that if I have 1 liter of A, I have X moles of A, right? I can express that molarity as that. It's because it's moles per liter. Does that make sense? Let's do it in a problem. All right, so for those of you health profession bound in here, once I get a problem, here we go. Your blood contains it contains 0.150 molar sodium chloride. Now I've got to couple the reaction with sodium chloride. It's not going to be a nice reaction because it's going to make a precipitate. So let's just go for lead. So if you ingest, and you shouldn't do this, ingest oh no, we're going to make a volume out of it. Let's just do a double displacement for this then. If you ingest got that wrong. Somebody help me with that? Or actually, hold on. Look at that. No. There we go. G. Thank you. If you ingest okay. Actually, let's go to grams with this. So we will go with lead. If you ingest 45 let's not make it that much lead. That would really kill you. Let's do 0.0045 grams of lead nitrate, lead 2 nitrate. How many grams of lead chloride are produced? Lead 2 chloride. Okay? So we're going to use this equation we have above. Let's go ahead and write that out. Sodium chloride, what's the formula for that? NaCl, right? And that's aqueous. And then we have lead 2 nitrate. So Pb, it's 2. How many nitrates do I put with it? 2, because nitrate has a charge of -1. Okay, and that's also aqueous, because all the nitrates are aqueous. Then we're going to do a double displacement reaction here, so we swap partners. And we're going to end up with lead chloride. Lead chloride is not aqueous, it's a solid. So not only would it be bad for you because it's lead, I don't know how that works. Because you do get lead. It must be that you get so much lead so little lead when you ingest lead. Because solids precipitating out in your blood is the sort of thing that'll clog up your capillaries and kill you. It'll give you an aneurysm or something else. So it must be that we just ingest so little lead that doesn't happen much. We'll talk about solubilities later. And then we're going to make sodium nitrate, which is also aqueous. Let me fix my nitrate. Okay, so sodium nitrate like that. Okay, so what we've got here is we need to balance our equation first, right? Shall we start with the leads? Leads are easy, right? So one lead and one lead. I'm going to do it in red because I'm going to erase those ones. I've now fixed how many chlorides I have. How many chlorides do I have on the side of the equation? 2. How many over here? 1. So I need to put a 2 in front of this. Okay, and now I fixed how many sodiums I have. How many sodiums do I have over there? I'm bouncing back and forth. And how many sodiums here? 1 or 2. Put 2 to fix that. I'll come back and erase my 1s. All right, my equation's balanced. So now now to solve this problem, it starts telling me, oh, there was never a volume in this. There's a molarity though. That's going to be in excess. Let's change. I'm going to have to change our problem slightly. So let's say it's a blood bag. What are those? Those are 100 milliliters, I think. 100 milliliters, we'll make it 3 significant figures, milliliters of your blood. There we go. All right. And then it says ingest, but let's pretend it's in a bag and you added it to it instead. The lead nitrate. Okay. So now we have a volume, right? Now we have a volume of sodium chloride, and we're going to go to moles of sodium chloride, and from there we're going to go to moles of lead chloride, and from there we're going to go to grams of lead chloride. Okay, does that make sense? And then we just need to come up with our conversion factors. Here we need to know what our formula weight is for sodium chloride. Somebody work on that for me. Okay, and then I need the ratios from my equation. Somebody not working on that, tell me what the ratio is. How many moles of sodium chloride make how many moles of lead chloride? 2 to 1, right? 2 moles sodium chloride equals 1 mole lead chloride. All right, and then here to go from moles of lead chloride to grams of lead chloride, I'm going to need the formula weight of lead chloride. All right, anybody get the sodium chloride formula weight for me? 58.44 grams of sodium chloride is equal to 1 mole of sodium chloride. Okay, and then anybody super fast and already done lead chloride?
278.1.
All right, 278.1 grams of lead chloride is equal to 1 mole lead chloride. All right, we're ready to do this. So we started out with 100 milliliters at a certain concentration, right? Whoops, actually, I lied, and I made you do extra work. We don't need that. We need our molar concentration, right? This is where our molar concentration comes in. We have a volume, but our molar concentration is 0.15 moles equals 1 liter, right? 0.150 molar means I have 0.05150 moles over 1 liter, right? Which I can rewrite as 0.150 moles of sodium chloride equals 1 liter sodium chloride. Does this make sense? This is really the new part for this problem. Questions on this part? Okay, now we're ready to finally do it. We've got all our constants, we've got all our conversion factors. We're starting with 100 milliliters of blood, right? So, this is actually a limiting reagent problem, but we're not going to be able to probably get that done. We'll see how far we go. So I start with 100 milliliters of sodium chloride, right? And then I'm trying to convert that. Actually, I put it in liters? To 100 liters. So I've got to convert that to liters, right? So there's 1,000 milliliters in 1 liter. So we have 0.100 liters of sodium chloride. So let's start our thing. We're going to go all the way across with that. 0.100 liters of sodium chloride. All right. And then I've got this conversion here that gets me from liters to moles. So if I have 1 liter of sodium chloride, I'm going to have 0.150 moles of sodium chloride. Right? Okay, so I've got my volume and now I'm at moles. Now I need to go moles to moles of lead chloride. And so our ratio there is this. 2 moles of sodium chloride make 1 mole of lead chloride. So 2 moles of sodium chloride equals 1 mole of lead chloride. Moles of sodium chloride equals cancels with moles of sodium chloride. Now I need to go from moles of lead chloride to grams of lead chloride. And we have that up here. That's this 278.1 grams of lead chloride equals 1 mole of lead chloride. So 1 mole of lead chloride is equal to 270, was it 1.88, 78.1 grams of lead chloride. Okay? All right, now we're ready to just go ahead and multiply across the top and divide by the bottom. Our answer, we have got grams of lead chloride. The actual problem didn't even ask us for a specific unit, which is great, so we'll just take the unit we get out the end. So we've got 0.1 times 0.150 times 278.1 divided by 2, and I've got 3 significant figures. I've got 2.09 grams of lead chloride. And I'm getting thumbs up from at least one person. Okay? The biggest part of that problem, the rest of it was just kind of all the stuff we normally do. But it was using this molar concentration right there to get from volume to moles. All right? All right. Well, I'll give you some of these for homework. You guys have a good weekend.